All right. How is everybody this morning? Doing okay? All right. Cool. So today we're going to start with a quick review of some of the things we talked about before. We talked about series circuits and parallel circuits. So we'll look at those and we'll look at some of the key facts about both of those types of circuits, because today we're going to be looking at another type of circuit called series parallel circuits. So it's just what it sounds like. It's circuits that include some elements in series and some elements in parallel. So the stuff that we already know about series circuits and parallel circuits is going to come back to help us here. So we'll talk about what series parallel circuits are, why we care about them, and then some of the key facts about those. And then we'll figure out how to calculate the equivalent resistance for series parallel circuits. Now, spoiler alert, it's not really anything new, okay? What we're going to do is we're going to use what we already know about series circuits and what we know about parallel circuits, and we're going to use those to find the equivalent resistance of parts of our series parallel circuit, and then we'll redraw the circuit and we'll just repeat that until we get down to one single resistor, okay? So we're just going to use what we already know, but we're just going to do it several times, okay? And I will do a couple of examples of that on the board. And then we'll go on and do a preview of today's lab. So today's lab starts on page 99 in the lab book, and we're going to have a little bit of everything. We're going to do some multi-sim, we're going to do some hands-on breadboard stuff, and we're also going to get to use these lamp boards. So these little boards that have lamps built in, we're going to get to play with those, okay? So that's our plan for today. Are there any questions before we get started? All right, cool. So then let's start with a review of series circuits. So remember, hopefully we remember what series circuits look like by now. You have several components connected together end to end, kind of like this. And how did we find the equivalent resistance for a series circuit? Like if this is 200 ohms and this is 50 ohms, what would be the total resistance for this circuit? 250, exactly. We just add those two resistances together. Okay? And we said that in series circuits, is the current the same for all components, or can it be different for components? It's the same, right. So the current is the same for all the components because any current that flows through R1 only has one path to take, so it all has to flow through R2 as well. There's only one way for it to go, okay? So the current is the same, but what about the difference? Right. What about the voltage? Can that be the same or can it be different? Does it have to be the same for all the components? The voltage? No, the voltage can be different. Remember, voltage is current times resistance. So if we have the same current but different resistances, we'll get different voltages, okay? So the current is the same for all the components in a series circuit, but the voltage may be different. Okay, so that's series circuits. Any questions about that? All right, and then we had parallel circuits. So parallel, we said that in parallel circuits usually have elements that are side by side. So maybe something like this. So if we have, say, a 2 kilo ohm resistor here, well, let's change that. Let's make that a 6 kilo ohm resistor there and a 6 kilo ohm resistor there. we know they're in parallel because the beginnings are connected to each other and the ends are connected to each other with nothing in between. Okay, that's the definition of parallel. And if I want to find the equivalent resistance for this circuit, do I just add those two resistors together? Get 12 kiloohms?
Right now, yeah.
What's that?
If it is like connected, yeah.
If they're in series, yeah, I would add them together to find the total resistance. But these are in parallel.
So like opposite.
Yeah, so we have to use a different procedure. So when resistors are in parallel and we add more resistors, do we get more total resistance or less total resistance?
Less.
Less, exactly, because we're giving that electricity more paths that it can flow down. So it's easier for it to move. So the more resistors we have, the more paths we give the electricity, and the less total resistance we have. So how would I find the equivalent resistance for a circuit like that?
Times we add and divide it by 2. Or
Yeah, so there's 2 resistors, so we divide something by 2. What do we divide by 2?
one of them.
One of the resistors, exactly. So we look at one of these resistor values, we see that that's 6 kiloohms, and there's 2 resistors. So we divide 6 kiloohms by 2, and we get an equivalent resistance of just 3 kiloohms. Okay? So in parallel, the total resistance for the circuit is always less than the smallest resistor in the circuit. Okay? So if the 2 resistors or 3 resistors or however many resistors you have, if they're all the same value, then we can use this formula to find their equivalent resistance. We just take one of those resistors and divide it by the number of resistors. However, if you have lots of 2 or more resistors in parallel and they're not all the same value, then we can't use this shortcut anymore. We have to use a different formula. Does anybody remember that other formula?
Ohm's law.
Almost. I like Ohm's law. Yeah.
Is it 1 over R1?
Yeah, exactly. So R total equals 1 over R1 plus 1 over R2 plus, and so on and so forth for however many resistors you have. Okay? So that's how we can find the equivalent resistance when you have different resistor values in parallel. Okay? So that's equivalent resistance in parallel. And now, in parallel circuits, we said that what do we know about the voltage? Does the voltage have to be the same for all these resistors, or can the voltage be different?
Same.
The same, exactly. So in parallel, the voltage is the same for all components. But what about the current?
Different.
Yep, that's right. But the current may be different. We know that the voltage is the same because, remember, voltage is the same along any wire. So that's true in any circuit, whether it's series or series parallel, any circuit you have, the voltage is constant along a wire. So imagine that we have a voltage supply here, and we connect it to a parallel circuit. Well, say we've got a 10 volt supply. That means that we can call this point down here ground. So that'll be 0 volts at that point. So then we have 0 volts all along this wire because voltage is constant along any wire. So we have 0 volts all along this wire. So we have 0 volts at the bottom of all of our components. And by the same token, we've got a 10 volt supply. So that means that we have what voltage up here at this point? 10 volts, exactly. So we've got 10 volts there. So then we've got another wire that's going all along the top of our circuit. So we must have 10 volts all along that wire. So at the top of every component, we have 10 volts. So we've got 0 volts at the bottom of every component and 10 at the top of every component. So that means that we have 10 volts across every component. So that's why we have the same voltage across all the components in a parallel circuit. But the current may be different if the resistor values are different, okay? So any questions about parallel circuits there? All right, so we did a quick review of series circuits and parallel circuits, and we looked at the key facts about both of those. And that's really helpful and important because today we're going to be talking about series parallel circuits. And these are circuits that include both series and parallel elements, okay? So let's move on and talk about that. So, like I said, what are series parallel circuits? They're circuits that are partially in series and partially in parallel. So why do we care about that? Well, really, almost any circuit in the real world is going to have some portions that are in series and some portions that are in parallel. I'll give you an example. When we look later in the semester, we're going to build a fiber optic communicator. Each one of you is going to get to build your own fiber optic communicator. So these are devices that have 2 boards, one that transmits your voice and one that receives your voice. So each of these devices is a series parallel circuit. And the way that it works, and what's common in many circuits, in fact, is that you'll have a power supply over here, and then that power supply will have long wires that go across your whole circuit. And then you'll have one section of your circuit right here that'll be connected to power, and then there'll be a resistor and there'll be some other components, and then down here it'll be connected to ground. And then next to it you'll have another section of your circuit that needs to get power, and then it's got some other stuff going on, and then it goes down to ground. And then you'll have another section that needs power and ground, okay? So each one of these sections, this section, all of the components in that section are in series. They're going from power to ground. But each of these sections is parallel to the other sections, okay? So this is a really common layout for circuits in the real world. You have power and ground going on these long wires so that they can supply any parts of your circuit that need power and ground. And then within your circuit, you have sections that start at power and go down to ground, and those sections are in series, okay? So this is a common example of a series parallel circuit, okay? So questions about that? All right, so that's why we care about it. We need to understand series parallel circuits so that we can understand other people's drawings and circuits when they design them, and also so that we can design our own, okay? So let's talk about some key facts for series parallel circuits. So in series parallel circuits, the sections that are in parallel have the same voltage across all of them. So like that example I just gave, if we had a 9-volt power supply, then each one of those sections would get 9 volts across it, 9 volts, 9 volts, 9 volts, okay? So the voltage would be the same for each of those sections, but the current could be different. And that's just like we have in a parallel circuit. Whereas in each series section, so like within one of those sections, the current would be the same throughout that entire section, because any current that starts at the top has to flow through all of the components and get to the bottom. So the current would be the same for section 1. For all the components in section 1, the current would be the same, but the voltage might be different across those components in section 1, okay? So again, we're just taking what we know about series circuits and parallel circuits, and we're applying those to the series parts and the parallel parts of our series parallel circuit, okay? So questions about that? All right, so let's talk about how we do the equivalent resistance calculation. So basically, what we do in a series parallel circuit is we look for any elements that are in series or in parallel, because we already know how to find the equivalent resistance for those sections. So if we see two resistors that are in series, then we find their equivalent resistance, and then we redraw that circuit, replacing those two single resistors with one equivalent resistance. Also, if we have two resistors that are in parallel, then we find the equivalent resistance for that pair and replace those two excuse me, with that single equivalent resistance. So let me do an example, okay? Hey guys, do you have a question back there?
Sorry, just figuring something out.
All right. Okay, so let's do an example. So let's say we have a circuit like this. We've got 20 volts here. And then okay, so we've got a circuit like this. So this is a series parallel circuit because it's not entirely in series and it's not entirely in parallel, but it has some elements of both. So like R1 and R2 are in series. We know that because the end of R1 is connected to the beginning of R2 with nothing in between. That's the definition of series, right? So R1 and R2 are in series. And then this section here is in parallel with this section over here. Because the top of this section is connected to the beginning of that section, the bottom of this section is connected to the bottom of that section. So this is a circuit that has some elements in series and some in parallel, okay? So that's a series parallel circuit. So let's try and find out kind of everything we can about this circuit. So we'll find out the total voltage, the total resistance, total current, and then the voltages and currents for each section. So V1, V2, V3, and then I1, I2, and I3. Okay? So we want to find out all of those things. So is there anything that we can write down before we have to do any calculations?
V total.
Yeah, V total, exactly. So we know that because that's the voltage coming from the power supply. So that's 20 volts. Perfect. So then what we've done in our other circuits is the next thing we do is we look at R total. We try and figure out the total resistance. So let's do that. So remember, we said that in order to figure out the total resistance for these circuits, we look to see if there are any elements in series or anything in parallel. So do we see anything in series or parallel here?
Yeah. Yes.
What's in series or parallel?
R1 and R2.
Yeah, perfect. So R1 and R2 are in series. And so we can find their equivalent resistance. So we'll say R1, 2, we'll call that the equivalent resistance of those two, is, how do we find the equivalent resistance for a series circuit?
Adding.
Yeah, we just add them together. So that is R1 plus R2. So that is 1 kilo ohm plus 3 kilo ohms. So that comes out to be 4 kilo ohms. So that's the equivalent resistance for that section of the circuit. So then what we can do is we can redraw this circuit. So we can say we've got 20 volts over here, and we've still got two sections in parallel, but now for this first section, instead of having two separate resistors, we're just going to have one equivalent resistance. So, and that equivalent resistance is going to be down here. So we'll call this R1, 2, and we'll say that that is 4 kilo ohms. Okay? So these two resistors together behave like a single 4 kilo ohm resistor. So we can redraw the circuit that way. And then we still have this other resistor over here on the right. And that's still R3 is still 4 kilo ohms. So these two circuits are equivalent, okay? So then now what we do is we just repeat that process. We look for any resistors that are in series or parallel, and then we combine those. So do you see any resistors that are in series or parallel here? Yeah.
Yeah, R1, 2, and R3.
Exactly. Yeah, yeah. So those two sections are in parallel. So then we find the equivalent resistance of those two. So can we use that shortcut to find the equivalent resistance, or do we have to use that longer formula here? Yeah, we can use the shortcut since both of these resistors are the same value. So, so we say that the equivalent resistance, we'll call that R1, 2, 3, or we'll call it R equivalent because that's, yeah. No, we'll call it R1, 2, 3 because we're combining those. R1, 2, 3 is 4 kilo ohms, the value of one resistor, divided by the number of resistors. So 2 in this case. So that comes out to be 2 kilo ohms. Okay? So that's our equivalent. So we could redraw this circuit like this. We would say we've still got the 20 volt power supply over here, and we've got now just a single resistor here. We'll call that R1, 2, 3, and that's 2 kilo ohms. And when we're down to just a single resistor for the whole circuit, that's the equivalent resistance for that circuit. So that's the total resistance. So we can write that over here in our answer. We can say the total resistance is 2 kilo ohms. So again, we're not really doing anything new here. We're just using our knowledge about series resistance and parallel resistance, and we're just applying that several times. So we looked at this circuit, we saw that R1 and R2 are in series, so we combined those two resistors using our series formula and found out that we just add those together to get 4 kilo ohms. So then we redraw that part of the circuit. So then we have 4 kilo ohms in parallel with 4 kilo ohms, and we can find the equivalent resistance of that using the shortcut, just dividing, since those two resistors are the same, we just divide one of them by 2, we get 2 kilo ohms, and that's the equivalent resistance for the whole circuit because that's just one resistor that represents the entire circuit, okay? So that's the general procedure. So any questions about that? All right, so then once we know the total resistance, now we have to look and try and figure out what to do next. So, any ideas about what we could do next here? Yeah, sure. Ohm's law. I love Ohm's law. Let's do some Ohm's law. V, I, and R. So what are we going to use Ohm's law for?
Current.
Okay, current. So which current?
Total.
The total current. Perfect. All right, so let's do that. So we say I total. That would probably, we cover that up. We see it's V over R. So that would be V total over R total. So we have those two things. So we can say that is 20 volts over 2 kilo ohms. So 20 over 2, that gives me 10, right? So that's 10 amps, is that right? Ah, yeah, right. I have to convert this 2 kilo ohms into 2,000 ohms. So that's 20 volts over 2,000 ohms. So that gives me 0.01 amps. And I could convert that into milliamps. I know that this comes out in amps because I put I did my calculation with everything in raw units. So I put in volts and ohms, so then the answer comes out in amps, okay? So I've got 0.01 amps, so that I can convert that into milliamps. So I'd move the decimal 3 places to the right, so that gives me 10 milliamps, okay? So that's my total current, so I can write that down. So I total equals 10 milliamps. And that's also the current, that means that that's the current that's coming out of this power supply. So we have 10 milliamps there. And since these circuits are equivalent, we must also have 10 milliamps over here. Okay, and how much current is going to be flowing back into the power supply? 10 milliamps. Exactly. We always have the same current flowing out of the power supply and flowing back in. It has to be the same. Okay? So, so that's what we have there. So then, what can we do next? That's always the hardest part for me, is figuring out where to go next. What information do I have that can help me solve something else? Yeah, so I would look at V3 here. So how could we figure out what is the voltage across R3 there?
20 volts is equal to this.
Yeah, that's right. That's right. It's 20 volts. And we know that because it's in parallel with the power supply. So we could call this point right here ground. So that would be 0 volts at that point. So then what would the voltage be right there? 0 volts, exactly. And over there, 0 volts. Perfect. And we got 0 volts down here, and then we got this 20 volt power supply. So that means we go up by 20 volts when we cross that power supply. So what's our voltage right there? 20 volts, exactly. And how about up at the top there? 20 volts, perfect, because it's along a wire and the voltage is constant along any wire. So how about over there? Again, 20 volts, exactly. So now we look at R3 and we see that we've got 0 volts on one side and 20 volts on the other side. So what's our voltage across R3? 20 volts, exactly. Perfect. So then we can write that down. So we can say the voltage across R3 is 20 volts. Yeah, oh, sorry, I wrote it in the wrong place. Thank you. Yep, 20 volts. All right. So then, can we say that there's 20 volts across R1? Because there's 20 volts there and... No, you're right. Because we got 20 volts at the top and 0 volts at the bottom, but some of that voltage is going to be across R1 and some of it's going to be across R2. So unfortunately, we can't just say what the voltage is across those yet. So then what could we do next? Yeah, the current, which current?
You have to split it from the last thing we drew, the smallest one with the 20 volts.
Yeah, perfect. So we could look at, that current through R3 because we know the voltage there and we know the resistance. So let's do that. So we'll say I3 equals, we cover that up, we see that it's V over R. So that would be V3 over R3. So V3 here is 20 volts. And R3 is 4,000 ohms. So what is 20 over 4,000?
5 milliamps.
Okay, so 0.005. Yeah. That doesn't look good. All right, 0.005 amps. So then I could convert that to milliamps. That would be 5 milliamps. Okay? So I can write that down. So I3 equals 5 milliamps. So that would be this current that's flowing down through there. 5 milliamps. Okay, perfect. So then we're back to this place where we're trying to figure out what to do next. So where could I go from here? Okay, yeah. So we could try and figure out the current that is going down this way. So how could we do that?
10 minus 5.
Yeah, that's right. So we've got 10 milliamps flowing through that wire there. We know that because we get 10 milliamps coming out of the power supply, and it all has to go there. So we've got 10 milliamps up there, and then we know that over here, how much current is flowing through this wire here? 5, exactly. We have to have 5 milliamps there because that's how much is coming down here through this resistor. So we got 10 milliamps over here. Only 5 of it is left going that way, so the rest of it has to be going down this way. So 10 milliamps minus 5 gives me 5 milliamps flowing down that way. Does that make sense? Okay. You could also think of it like cars on a road. So say you've got 10 cars driving down this road, you come to an intersection, and only 5 of them continue on this way. The other 5 must have come down this way, okay? So that's another way to think about it. So we got 5 milliamps flowing down this path. So how much of that goes through R1?
5.
All of it, right? Because this is only the only path for it to go down. Yeah, and how much goes through R2?
5.
5 also, because again, there's only one path for all of this current to take. It's like if you had one road and you saw 5 cars coming down at the top, you would know that there was 5 cars in the middle, and then you'd have to have 5 cars driving out the bottom also. So we got 5 milliamps for both of these resistors. So then we can write down our currents over here. So I1 is 5 milliamps, and I2 is 5 milliamps, okay? So, all right. So then once we know those, we know the current and we know the resistance for those two components, so we can use Ohm's law to figure out the voltages. So for R1, we would say V1 equals, and then we cover that up. We see that it's I times R. So then I1 is 5 milliamps, or 0.005 amps, and then R1 is 1,000 ohms. So that gives me 5 times 0.05 times 1,000 is 5 volts. So we have 5 volts across that resistor. So now we could do the same thing. We could use Ohm's law for R2 to figure out that voltage, but there's also another way we could do it. Can anybody see another way we could figure out that voltage?
Nice. Subtraction.
Yeah, we could look at subtraction, because we know that we have 20 volts at the top here and 0 volts at the bottom there. So there has to be a 20 volt difference from there to there. And we know that from there to there, we've only gone 5 volts. So the rest of it has to be across this resistor. So together, these have to add up to 20. So we've got 5 there, so we must have 15 volts there. Okay? Any questions about that? All right, so then we know that V1 is 5 volts and V2 is 15 volts. Okay? All right. So I know that was kind of a lot of math, but that is how we can do some series parallel calculations to find the voltage and current in a series parallel circuit. Okay? So any questions about that? Okay. All right. So then let me do one more example here. So let's say that you have a circuit and you've got 36 volts over here, and then a resistor at the top that is 4 kilo ohms, and then one over here that's 6 kilo ohms, and down here you've got 6 kilo ohms, and then over on the right, you've got another resistor, and this one is 3 kilo ohms. Okay? So we'll call this R1, R2, R3, and R4. Okay? So let's try and find the equivalent resistance for this circuit at least. So do we see any resistors that are in series or parallel? Well, first of all, let me say that it's tempting to say that R1 and R2 are in parallel because they're kind of side by side, right? So they look like they're in parallel. But remember, the definition of parallel is that the beginning of each resistor is connected to the beginning of every other resistor with nothing in between. And in this case, that's not really happening because the beginning of this resistor is not connected to the beginning of this other one. We have this power supply in between them, okay? So that's a problem. Also, the ends of the resistors have to be connected with nothing in between for parallel. And in this case, between the end of R1 and R2, we have this other section here. We have R3 and R4. So even though R1 and R2 are kind of side by side, they're not actually in parallel, okay? So that is something that could trip people up on this circuit. So do we see any other resistors that are in series or parallel though? Yeah.
Aren't R1 and R3 in parallel? With
R1 and R3? Well, they look,
R3 and R4.
yeah, so R1 and R3, yeah, they look tempting, right? Because the end of R1 is connected to the beginning of R3. So it looks tempting, but R4 is connected, in between them. So they're not actually in series because they have this other thing in between. So then R3 and R4 are in parallel because the beginnings of the resistors are connected to each other with nothing in between, and the ends of the resistors are connected together with nothing in between. So R3 and R4 are in parallel. So we can find their equivalent resistance. So in order to do that, can we use that shortcut formula that we had? No. Right, because that only works when the two resistor values are the same. So we have to use that longer formula. So then we say that we'll call that R34 equals, we use that longer formula. So it's 1 over R1 plus 1 over 1 over R3 plus 1 over R4. Okay, so that's the formula that we have to use. So then that's 1 over 6 kilo ohms plus 1 over 3 kilo ohms. So what's 1 over 6 kilo ohms? 1 over 6,000. Does somebody have a calculator? Let me get this out of the way. 1 over 6,000? Can somebody help me out?
0.0016.
Okay, so that's 0.0016, and then 1 over 3,000?
It's 30.
Oh, 3 zeros, thank you. 0.00016, and then 1 over 3,000? It's probably twice that, so 0.000333 repeating. All right, so what do I get if I add those two together? I get 1 over 0.0005, right? So then, if I do that, if I divide 1 by 0.0005, that gives me 2,000 ohms, okay? So that's the equivalent resistance for R3 and R4 combined. So then we can redraw this circuit. So we would say we've still got the 36 volt power supply over here. We've got 4 kilo ohms up there. 6 kilo ohms down there. And now over here, we're left with the equivalent resistance. So that'd be R34, and that's 2,000 ohms. Okay, so we took R3 and R4, we combined them, we found their equivalent resistance, and we redrew the circuit with that equivalent resistance of 2,000 ohms. So any questions about that? All right. So then we just repeat that process again. We look for any elements that are in series or in parallel, and then we redraw the circuit combining those elements. So do we see any resistors that are in series or in parallel?
All is in series?
Yeah, they're all in series, because remember, the definition of series is that the end of one resistor is connected to the beginning of the next with nothing in between. So the end of R1 is connected to the beginning of R34 with nothing in between. The end of R34 is connected to the beginning of R2 with nothing in between. So they're all in series. And to find series resistance, we just add the resistors together. So we can say that R 1, 2, 3, 4 equals R1 plus R2 plus R3, 4. So that's 4 kiloohms plus 6 kiloohms plus 2 kiloohms. So that comes out to be 12 kiloohms. So that's the total resistance for our circuit. So we could redraw that like 36 volts still, and then just one single resistor that is 12 kiloohms. Okay? So that's how we can find the total resistance for that circuit. So any questions about that? Okay. Does anybody want me to go on and find the voltages and currents for this circuit, or are we good for now?
Yes.
Yeah? All right. All right, let's do it.
Mind if I take a quick photo before you race off?
Go for it. Go for it. Yeah.
Alright, good. Thank you.
Sure. All right. All right, I'm kind of glad that we're going to do the voltages and currents here, actually, because this is very much like the circuit that you're going to have on your midterm, okay? So your midterm circuit is going to be in this configuration. You're going to have 4 resistors in this layout. Your resistor values will be different than these resistor values, but the shape will be the same. So the general procedure will be the same, okay? So, so let's write down what we're trying to find again. So V total, R total, I total, and then V1, V2, V3, and V4. And then I1, I2, I3, and I4. So we're trying to find all of those things. So it's kind of a lot, but I think we can do it. So, all right, so what do we know so far? Yep, we know the total voltage, right? That's the 36 volts from the power supply. And what else? Yeah, the total resistance. That's what we calculated up here. So that's 12 kiloohms. So then, so what could we find next? Yeah, we can find the total current because we know the total voltage and resistance. So let's do that. So we use Ohm's law again. We write down I total equals V total over R total. So that gives me the V total is 36 volts, and then R total is 2,000 ohms. So yeah, so that gives me 0.012 amps, which is 12 milliamps. So that's the total current. So any questions? Oh, I'm sorry. Thank you. Thank you. I'm screwing that up. All right. 36 over 12,000 ohms. So that gives me, yeah. 0.003 amps. So that is 3 milliamps. Did I get that right?
Yeah.
All right, cool. All right, so then the total current, I total, is 3 milliamps. So that's the current flowing out of our power supply. So we've got 3 milliamps there. So then how much current is flowing back into this power supply?
3 million.
Exactly, because we always have to have the same flowing out and flowing back in. So, so what can we figure out next about our circuit here? Yeah, so exactly. So how could I find I1 here?
Ohm's law.
I always like Ohm's law, but in this case, I don't think we even have to go there. So,
If we see the second circuit that we made,
this one?
yeah, that's in series. And
Uh-huh.
we can easily find I1 and I2 and I3 for
Okay. So how would we do that?
series circuit.
Yep.
I1 is equal to all the wires.
Yeah, you're right. Okay, perfect. And we know that, so the current has to be the same for all of the components, and we know that the total current is 3 milliamps. And so, yeah, so that has to be the current for all of those components. So yeah, that's a good way to look at it. Yeah.
And after we do that, when we go back to the main diagram,
Uh-huh.
for R3 and R4, you split the current, right?
Yeah, so some will go through R3 and some will go through R4. Yeah. So here we have 3 milliamps. So we know that our I1 is 3 milliamps. And then I2 must also be 3 milliamps. And then you could say I34 would be 3 milliamps. So that's the total of the current going through R3 and R4. But yeah, it splits like you said, and it doesn't split evenly because these are different resistor values. So we can't just say that half is going to each one. If they were the same resistor values, then it would divide evenly. But so yeah, we can't just divide it evenly here.
You can find V1.
Yeah, so we can look at the voltage across R1 because we know the current and we know the resistance. So we can say that V1 equals, we cover that up, we see that it's I times R, so that's I1 times R1. So I1 is 3 milliamps, or 0.003 amps, and then R1 is 4,000 ohms. So what does that give me? 12 volts, okay. 12 volts. So we know we have 12 volts there, and V1 over here, we can write down is 12 volts, okay? And then I can do the same thing for R2. So I can say that V2 equals I2 times R2. So then I2 is still 3 milliamps, so 0.003 amps. And then R2 is 6,000 ohms here. Bless you. So what does that give me? 0.003 times 6,000?
18.
18. Okay. So that gives me 18 volts. So across here, we have 18 volts. And I can write that down over here. So we've got V2 is 18 volts. Okay. So then, now we come to kind of a tricky part. We have to figure out, again, what we're going to do next. So, any ideas?
We know the voltage at R3, R4.
Okay, so we know that voltage. So,
36 minus 12.
Okay, so that's a good way to do it. So yeah, so we can look at that. So we could call this point down here ground. So then, yeah, we'd have, we'd say that voltage is 0 volts at that point right there. And then we go across our power supply, and that's a 36 volt power supply. So yeah, so we go up by 36 volts. So that means that we have 36 volts at that point. But then, yeah, we have this other resistor here, and we know that there's a 12 volt difference across that resistor. So this side is 12 volts higher than that side. And we know that this side is 36 volts. So what would be the voltage at that point right there? 24, exactly. So we got 24 volts there. Also down here, we know we've got 0 volts here. But now we've got an 18 volt difference across this resistor. So we're at 0 volts on the left of the resistor, and there's an 18 volt difference. So what voltage do we have to have on the right side of that resistor? 18, exactly. So now we know that on this, for R3 here, we have 24 volts on one side and 18 volts on the other side. So what is the difference then across that resistor? Yeah, it's 24 minus 18, or 6 volts, exactly. So that's how we could figure out, that's one way to figure out the voltage across R3. So any questions about that? And then we could also have looked at it another way. Like I said before, in electronics, there's often many different ways to find the right answer, and it's often helpful to know more than one so you can use whatever is easiest in a given circumstance. So another way we could have looked at this is we could have looked over here, and we could have said that, okay, we've got 3 milliamps flowing through here, so that's 3 milliamps flowing through R34, and R34 is 2,000 ohms. So we could have used Ohm's law there. We could have said V equals I times R, so that's 3 milliamps times 2,000 ohms. So that would give us 6 volts there. And since these resistors are in parallel, we know that the voltage has to be the same across them. So we'd have 6 volts across each resistor. Okay? So that's two different ways that we could have found that answer. So any questions about that? Okay. So now the last two things to find are I3 and I4. And so for those, we know the current. I'm sorry, we know the voltage and we know the resistance, so we can find the current. So we can use Ohm's law again. So we can write down I3 equals, cover that up, we see it's V over R. So V3 over R3. So that V3 is 6 volts, and then R3 is 6,000 ohms. So 6 over 6,000 equals 0.001 amps, which is 1 milliamp. So that means that we have 1 milliamp flowing that way, down this resistor there. So we could use Ohm's law again for R4, but is there another way we could find the current through R4?
Yeah,
Yeah, what could we do?
we have 3 milliamps to count on that.
Yep, so we have 3 milliamps up here, exactly.
1 milliamps goes down and
Yep.
the rest goes to R.
Exactly. So 3 milliamps up here, 1 milliamp comes there, so the rest of it has to go this way. So 3 minus 1 gives me 2 milliamps going that way. So then we can write those down. So I3 is 1 milliamp and I4 is 2 milliamps. So questions about that? Okay, bless you. So one other thing to note, I pick resistor values here on the board so that my currents come out and my voltages come out in nice, even, round numbers. I do that because I think it's easier for you to see what's going on and understand. You know, okay, I've got 3 milliamps up here, one of it goes down there, so then 2 of it has to come that way. I think it would be less clear if I said I got, you know, 4.7862 milliamps here and 1.837 goes down this way, so then, you know, 1.89 whatever is left going that way. It's harder to see what's going on, I think, if the numbers are really weird decimals. So that's why I pick numbers that come out nice and cleanly. But when you're doing real circuits, the numbers will almost never come out in nice, round, even values, okay? So they will almost always be decimal numbers. I say this because last semester I had a student come up to me and say, you know, I was doing my test and I was freaking out, and I knew I was doing something wrong because my numbers came out all weird and your numbers always come out real nice on the board, and so I knew something was wrong. And it's like, no, I do that. I pick those numbers carefully, the resistor values and the power supply voltages carefully, in order to make this happen, so that hopefully the numbers are a little bit easier to see and the math is a little bit easier to do. You know, it's kind of easy to see that 18 volts plus 6 plus 12 comes out to 36. It's harder if there's decimals, but your numbers will come out almost certainly with decimal values, and that's okay, all right? So any questions about how we found these values here? Okay. So those are a couple of examples of how we can use Ohm's law to find voltages and currents in series parallel circuits, okay? So again, the general procedure was that we looked at the whole circuit, we looked for series or parallel elements, we reduced those elements, and then we repeated that until we were down to just a single resistor value, and that was the equivalent resistance for the whole circuit. And then once we had that, we could find the total current, and we could find, we could use that and kind of use what knowledge we had to find the other values in the circuit. Okay. Now, each circuit is going to be a little bit different. Each one's going to be a little bit different shape. You're going to have different things given to you. So it's going to be a little bit of a puzzle each time. You're going to have to kind of figure out where to go with the information that you have. It's going to be a little different each time, but this is a couple of examples of those types of calculations. So any questions before we go on to our lab preview? All right, so then let's go on and do a preview of today's lab. All right, so today's lab starts on page 99 in the lab book, and what you have here is you have a series parallel circuit in multisim. So you can see you've got two branches. The left branch is called branch A, and the right branch is branch B. And each one of these has two resistors in series. So if you have a 1 ohm resistor in series with a 1 ohm resistor, what would be the equivalent resistance for branch A here? Yep, so this would be 2 ohm equivalent resistance. And you got the same thing over here on the right, so this would also be a 2 ohm equivalent resistance. Bless you. So then if we have 2 ohms in parallel with 2 ohms, what would be the equivalent resistance for those two branches in parallel? 1, exactly, because we've got two resistors, the same value. We just take one of those resistors, divide it by 2. So the equivalent resistance for this whole circuit should be 1 ohm. So that's what you're going to do. That's what we're going to do in this table down here. You'd say that branch A resistance is 2 ohms. You would just calculate that. And branch B is also 2 ohms. And then you would use multisim, and you would run the simulation and look at the value on this meter, and then that would give you the equivalent resistance, the total resistance for that circuit. And hopefully that will come out to be 1 ohm. Okay? So you would do that with your simulation. And then you would go on and you would change the resistor values. So the next time you would make all of the resistor values 2 ohms. And then you would find the branch resistances and the total resistance for that circuit. Okay? And you're just going to go through and do that for the entire first table here. So you'll do that for different resistor values up to 6 ohms. Okay? So all right. So what's going on here? So I think that there's a question about how this came out to be 1 ohm. So what happens is that we're just going through here and we're doing what we did on the board. We're finding resistors that are in series or parallel, and we're combining those. So the first thing that we see is R1 and R3 are in series. So we can redraw those as one single equivalent resistance. So that would be R1 and R3 together. They're in series, so we just add those together. So that would be 2 ohms. And then the same thing for the other side there. You have R2 and R4 in series, so we can add those together. So that's also 2 ohms. So then you have an equivalent circuit that looks like this. We've got 2 ohms in parallel with 2 ohms. So then we want to find an equivalent resistance for that circuit. So if we have 2 resistors in parallel and we want to find their resistance, if they're the same value, we can just take one of those values and divide it by the number of resistors. So that would be, one of those values would be 2 ohms. And then we have a total of 2 resistors. So that comes out to be just 1 ohm. Okay, so the equivalent resistance here, if we were to draw this as just a single resistor, that would have a resistance of 1 ohm. Okay? So any questions about that? All right, so then you're going to go on and do that for the rest of the table down here. And then the next part in the lab is another circuit in multisim. So you can see with this circuit, this one actually has 3 branches. So you're going to do kind of the same thing. You're going to calculate the equivalent resistance for each branch. So in this case, you've got 1 ohm in series with 2 ohms. So what is that equivalent resistance? Yeah, so that would be 3 ohms there. And then you've got 2 more branches that are the same. So you'd have 3 ohms on the left, 3 ohms in the middle, and then 3 ohms on the right here. So then you'd have an equivalent circuit that looked like that. And then if you wanted to find the total resistance for that circuit, what would you do? Yeah, you'd take since all of these resistor values are the same, you'd take one value, so 3 ohms here, and then you divide it by the number of resistors, so that would be 3, so that comes out to be 1 ohm. So the equivalent resistance for this whole circuit would be 1 ohm. Right, so you would write down the branch resistance for each of these branches, and then you would use multisim, again, to simulate this circuit, and you'd look at the value that's on this meter, and then that should tell you the total equivalent resistance. And you can write that down over here. But hopefully, it'll come out to be 1 ohm, like we calculated. Yeah?
Question. So the R1 and R3 are 1 and 2. There's no 1 and 2 for any of them. They're all matching 1, 1, 2, 2, 3, 3 on the branch A, B, and C.
Oh, you're right. So that's a good point. So right up here in this circuit, the way it's drawn, it shows 1 and 2, but down here it doesn't. It shows 1 and 1. Yeah, that's what I would say. So you can start with this circuit, but then put in these values. So yeah, so you'd have 1 and 1. So then if we were doing 1 and 1, you wouldn't have 3 ohms for these branches.
6
Yeah, so you'd have, so 1 ohm and 1 ohm, that would give you 2 ohms, huh? 2 ohms for each branch. And then, so what would be the equivalent resistance for that circuit? Yeah, so you would take the value of 1 resistor, so that would be 2 ohms here. And then you divide it by the number of resistors, so that would be 3 resistors. So,
0.67.
yeah, 2 divided by 3 equals, yeah, 0.6667, like, 7 at the end there. Yeah, so, so that would be the equivalent resistance there. Okay, so hopefully that's what you would see on your simulation. And then you change the resistor values to 2 ohms each, and you repeat that and fill out the rest of the table there. So yeah, questions about that? Okay. So yeah, good observation there. I missed that. All right, and then going on here, all right, this next part is a little bit tricky. It's not really necessarily clear what's going on. So let me pull up this part in Multisim. So we'll go here to Open File Explorer, and we'll go to Instructor Files, and then ET302, and then this is L17 series parallel. And then this one is circuit 7C1. Okay, so it looks like we have 3 different circuits here, but really what's going on is we're just thinking about this first circuit, and we see that this is a series parallel circuit, and what we want to do is that we want to analyze what's going on inside this series parallel circuit, and we want to find the equivalent resistance for this series parallel circuit. Circuit 1, okay? So the way that we would do that is we would look for elements that are in series or parallel, and we see that branch A, the resistors in branch A are all in series. The resistors in branch B are in series, and the ones in branch C are in series. So we would redraw each one of those branches as an equivalent resistance. And that's what's going on. So over here, circuit 2 is really just circuit 1 with all of the branches redrawn with a single resistor, okay? But right now, if we run the simulation, let's look at the currents. So this is current 1, and this is current 2. So we'll put these in current measuring mode. We run this simulation, and we can see that right now the currents don't match. So that means that these circuits are not equivalent right now. So what's happened is that this circuit 1 has been redrawn, but the equivalent values are wrong, okay? So what we need to do is we need to make circuit 2 match circuit 1. So we need to look at the resistors in branch A here, and then make branch A of circuit 2 match the equivalent resistance for branch A of circuit 1. So what would be the equivalent resistance for branch A here? Yeah, we can see that the equivalent resistance for branch A is 8 ohms because we got 6 ohms plus 2 ohms. So then we would come over here and we would make this branch A equal to that one. So we would say that this is 8 ohms, okay? And then the same thing for branch B. We look at branch B, we see that it's 4 ohms in series with 4 ohms, so that would give us 8 ohms. And then for branch C, we have 2 ohms in series with 2 ohms. So what's the equivalent resistance there?
4.
4. So we'd come over here and we'd make that 4 ohms. Okay? So now when we run the simulation, hopefully these currents will be the same. Let's find out. Yeah. So now they're the same because we've made circuit 2 match circuit 1. We've made them equivalent circuits. Okay? So that's what's going on. We're just really trying to examine circuit 1 and we're simplifying it and making sure that our simplifications match up. So we've simplified that to circuit 2 now. And so then the final thing is we would look at all the branches in circuit 2 and we see that they're all in parallel. So then we'd try and find the equivalent resistance for those 3 branches and then make that the equivalent resistance down here. So you would do that. You'd use your formula to find that equivalent resistance and then make that the equivalent resistance down here. And then when you run your simulation for circuit 3, hopefully that current would also match the current for circuits 1 and 2. Okay? So that's what's going on here. We're analyzing circuit 1, and these other 2 circuits are just kind of steps on the way to finding that equivalent resistance. Okay? So questions about that?
What program is that?
That's in Multisim. It's circuit 7C1 in Multisim. It's under L17 series parallel lab.
L17.
Yeah, it's written down here in the lab book. Circuit 7C1 in series parallel. Okay. So then, so yeah, in the lab book it says to look at those 3 circuits and then find the total current. And it says print out the multisim circuit, but you don't have to do that. Okay, so you can cross that out. You don't have to print that out. All right. So that's that part. And then the next part in the lab is very similar, but you're going to use start with slightly different values. You're going to use a different circuit there. All right, so any questions about the multisim part? All right, then let's go on and look at this part. And you'll notice, again, this is very much like the circuit that we did on the board. It's the same shape. It's the same pattern. The resistors are in the same place, okay? And again, this is important to look at this because this is what we're going to be doing on the midterm. You're going to be building a circuit in this shape, and you're going to be using your meter to find the voltages and currents in this circuit. And you can also use circuit math like we did on the board to check your work, okay? So definitely take your time with this one and make sure you really understand how to put it together and how to make all those measurements, because this is what you will be doing on the midterm. So we're going to build this circuit on a breadboard and then find the voltages and currents for all of the circuits, or for all of the components. So let me show you one way to do this on a breadboard, okay? So let me grab a breadboard here. All right. So again, there are many different ways that you could build this circuit on a breadboard. But when I build a circuit, I like to make it look kind of the same on the breadboard as it does on the diagram. That way, it's harder for me to get confused. I can still do it, believe me, but it's a little bit harder to get confused, okay? So what I see in this diagram is I've got the 12-volt power supply coming in on the left. So I'm going to put the positive jumper wire for the positive side of the power supply there, and a jumper wire for the negative supply down here. So I'm using these long rows that run all along the sides of the breadboard, okay, for the power and ground. Now I see that R1 is connected to the positive side of this power supply. So when you build this circuit, you want to make sure that the resistor you're putting in this place is the 1 kilo ohm resistor. Okay? If you put the wrong resistor in here, you're going to get the wrong values. So you're going to put this resistor, I would put it here like this. So one side is connected to the power supply, and then R2 is going from R1 down to R4. So I'm going to put a resistor from there to there, and then R4 is coming here from the bottom of R2 back to the negative side of the power supply. So I'll put a resistor from there down to there. Okay, so now I've got R1, R2, and R4. The last thing I need is R3. So I'm going to put this one I look at the diagram and I see it's kind of on the right side of the picture. So I'm going to put it a little bit on the right side of the board here. Kind of like that. But now, the top of R3 is connected to the top of R2, and the bottom of R3 is connected to the bottom of R2. I haven't made those connections yet on my board, so I need to put those connections in. So I'm going to do that with a jumper wire. So I'm going to put that in there, and that side of the wire in that spot there. And you want to make sure that you really push that wire down so that it gets to the bottom of the board so it makes a good connection, okay? You should feel it kind of slide into the spot a little bit, and it shouldn't be easy to tug out. So that's the connection from the top of R2 to the top of R3, and then you can do the same thing for the bottom. So I'm going to make this wire go from the bottom of R2 push that in and go to the bottom of R3. All right, so that's how I would make this circuit on the breadboard, okay? There are 1,000 different ways that you could do this. You're welcome to do them in any way that you want, as long as you get the right values. But I like to do it this way because it makes the circuit on the board look like the circuit on my diagram. So I know that if I want to look at values for R1, that's the top resistor in the diagram, so it's going to be the top resistor on my board. If I want to look at R3, that's the rightmost resistor in the diagram. It'll be the rightmost on my board. Okay, it just keeps things straight in my head that way. All right, so then once you have the circuit, you need to measure the voltage and the current for that circuit. So remember, when you're measuring voltage, that's a non-destructive measurement, so you don't have to take the circuit apart at all to make voltage measurements. So to measure the voltage across R1, you could just touch the two leads of the meter to the two sides of R1. Okay, so you would just touch the two leads of the meter there. And you could repeat that for all of the resistors. So that's how you measure voltage. It's relatively easy. Measuring current is a little bit trickier. Remember, to measure current, you have to partially deconstruct the circuit. You have to take it apart a little bit. So remember, the way that I do that is that if I want to measure the current through a resistor, what I'll do is I'll take one lead of that resistor out of the board. So I've broken that circuit apart, and now there's two loose ends of that circuit, and I have to hook those two loose ends of the circuit up to the two leads of my meter. So one loose end should be relatively easy to see. It's the end of this resistor. The other loose end is where that resistor was connected. So that'd be that hole in the board, and you can't hook your meter to a hole. So what you have to do is you have to put a jumper wire into that hole. And then once you have that jumper wire attached, that is the other loose end of your circuit. So you'll hook those two loose ends of your circuit to the two leads of your meter. So one lead goes to this jumper wire that's sticking out, the other lead goes to this resistor. Then you put your meter in current measuring mode, you measure the current, and that's your value. And then when you're done with that measurement, make sure you put your circuit back to how it originally was before you go on to anything else. There's a temptation to just kind of jump right into the next measurement, but that usually leads to trouble because something isn't hooked up right, and then you end up with the wrong value. So make sure you put your circuit back to its original shape before you make the next measurement, okay? So that is back to its original shape, and then you could go on and make the voltage or current measurement that you want to do next, okay? So the last thing is this total voltage and the total current here. So to measure the total voltage, that's the voltage coming from the power supply. So that's the voltage from one side of the circuit to the other. So you could do that by sticking two jumper wires into your board, one at one side of your circuit and the other one on the other side of your circuit, okay? And then hook your meter up there and measure the voltage that way. So that's how you could measure total voltage. For total current, that's the current coming out of the power supply, remember? So in order to measure that, you would have to break your circuit apart right where the current comes in from the power supply. Well, the current is coming in from the power supply at this red wire. So what you could do is you could pull this red wire out of the board, and then that would be one loose end of your circuit. You could put a jumper wire into the board where that red wire was connected. That would be the other loose end of your circuit. And then you hook those two up to your meter and measure the current through those wires, and then that would be the total current for your circuit, okay? And then when you're done, of course, you take the jumper wire out, you put everything back the way it started, and then you're ready to make any other measurements for your circuit. So that's how you can measure the total voltage and the total current for your circuit. So any questions about that? All right, and then the last part in today's lab is the lamp board. So you're going to measure, you're gonna set up a lamp board, and you're gonna make some measurements here. So this is a little bit tricky to set up this lamp board. So let me show you how we're gonna do that. So first of all, you need the lamp board itself. So we have a box up here at the front with the lamp boards in it. The boards are just boards by themselves. They don't have these little light bulbs screwed in. The light bulbs are separate. We keep them separate because if we had them all together and they were all in this box, they would just get smashed and the light bulbs would break. So you'll have to grab a board and then 3 bulbs as well. And when you're done with them, please take the light bulbs out and separate them from the board. So then what you're going to do here is you're going to hook up your lamp board so that it matches the circuit that is shown in your book with one small change. And that is that in your lab book, the circuit shows 4 lamps, but we only have 3 on this board. So you're just going to cross out this bottom lamp and treat that like a long wire, okay? Just so you can cross that out in your lab book, all right? So now let's look at how this circuit is set up in the book and see how we can make those connections on the board itself. So I'm going to start with L2 and L3 here. Because the top of L2 is connected to the top of L3, the bottoms are connected together also. So we can make those connections with these alligator wires. They have alligator clips on both ends. So we're just going to connect the top of lamp 2 to one side of an alligator wire. Top of L3, we're going to grab in the other side of that same alligator wire. So we make that connection there. And then we can do the same thing for the bottom of L2 and L3. All right, so we made that connection there. And now the next thing shows that one side of L1 is connected to the top of L2. So over here we have L1, so we'll connect one side of L1 to the top of L2. Again, we're just using a jumper, an alligator wire here to make that connection. All right, and then finally, the other side of L1 is connected to the positive side of the power supply. So I would take a jumper wire, an alligator wire, and connect that there. And then the other side of L2 is connected to the negative side of the power supply. Okay, so I'm sorry, and see, I screwed this up too. So the side of L1 that's not connected to L2 connects to the power supply, okay? It's easy to screw this up because the power supply is up. Anyway, the thing to notice is that the side of L1 that's not connected to L2 goes to the power supply. So that would be this side down there, okay? So that side of L1 goes to the power supply, and then the bottom of L2 goes to the negative terminal of the power supply. So I would use a negative alligator wire and connect that side of L2 to the power supply. Okay, so that's how you create your circuit. Okay, so it's a little bit tricky, but I think you can do it. And now let's look at the current that's going to be flowing through this circuit. So we have some current flowing out of the power supply. How much of that current is going to flow through L1? It's going to be all of it or just part of it? All of it, exactly, because the current that flows out of the power supply only has one place to go. It all has to go right through that light bulb. So L1 is going to be pretty bright because it's getting all of the current. But then that current is going to come along and it's going to come to this junction here. So it's going to split off. And part of it is going to go to L2 and part of it is going to go to L3. So are L2 and L3 going to be as bright as L1?
No.
No, they're going to be dimmer because they're each getting only part of the current. So when you hook this circuit up, you should see that L1 is burning pretty brightly, but L2 and L3 should be significantly dimmer, almost to the point where it might be hard to see that they're on at all, okay? So that's one way to check that your circuit is working properly, okay? And then once you have your circuit up, you're going to measure the voltage and the current for the lamps, as well as the total voltage and total current down there. So, any questions about that? All right, so that's our lab for today. So then I will take attendance and then I'll let you go.